Good morning, everyone. So as Dr. Leonard introduced, I'm going to be presenting a joint work with Professor Hailong Dao at the University of Kansas. And first of all, I would like to thank the organizers for this wonderful opportunity. Now, without further delay, let's proceed. Are you able to see my cursor on the screen?
Yes.
Okay, thank you. So, first of all, these are the contents. So I would just give a brief introduction of what a simplicial complex is and the Stanley-Reisner correspondence, from where we would move on to the construction of the ideal which we are going to be dealing with in our project, and then a brief overview of what you mean by the Lefschetz properties, followed by one such application in the case of pseudomanifolds. So to begin with, what is a simplicial complex? We have a finite collection of vertices, and say we have n vertices. And so the abstract simplicial complex on that collection is defined as a non-empty subset of the power set of V. So it's basically a collection of subsets of the set V, which has a special property of inclusion. That is, if you have any set in this simplicial complex delta, then all the subsets of that set will also be an element of the simplicial complex. So for instance, we'll go to an example, but before that, I want to define some of the terminologies which will be relevant in this talk. Now, what do we mean by the faces? So the faces of a simplicial complex are basically the elements of a simplicial complex. And since these elements are basically subsets of the vertex set, we can count the number of vertices in each faces. And so if we have k plus 1 vertices, we would call it a k face or a k simplex, or we would say the dimension of that face is k. Now, the faces which are maximal with respect to inclusion are called facets, and the dimension of the simplicial complex itself is the maximum possible dimension of a facet. And the T-skeleton, which will be a term we'll be using later, of a simplicial complex is basically the set of all faces of dimension at most D. Now, proceeding further, the F vector of a simplicial complex is basically giving you the information about how many faces are there of each dimension in that simplicial complex. To move on to an example, whenever we're defining a simplicial complex, we would usually define it by just mentioning the maximal faces or the facets. For example, in this case, we have a complex given by the triangle 1, 2, 3, and then the edge 3, 4. So the faces of it would be all the vertices, the edges, and the whole triangle. And of course, the empty set is also part of the simplicial complex. Now, given such a complex, let us consider what is the Stanley-Reisner correspondence. Now, we have a vertex set consisting of n vertices. Now, based on that, we are defining a polynomial ring on n variables over a field of characteristic 0. And we are defining the ideal, I delta, as the ideal defined by the monomials, which are the non-faces of the simplicial complex. So by non-faces, what we mean is, for instance, in this particular example, 1, 4 is not part of the simplicial complex, or 2, 4 is not part of the simplicial complex. So these edges which are not part of the complex will feature in the definition of this ideal, x1, x4, x2, x4. So, and then this ideal is called the Stanley-Reisner ideal or the face ideal of the complex. And the quotient we obtain from that is a Stanley-Reisner ring or the face ring of this complex. Moving further from here, for our project, we slightly modify the Stanley-Reisner ideal. So what we do is we take that ideal and we also adjoin the squares of the variables present in it. And thus we are getting a quotient ring, which is actually an artinian monomial algebra. So for example, for the previous case, we had the ideal generated by x1, x4, and x2, x4, the monomials. To that, we adjoin the squares of the variables as well. Okay. Now, some invariants of this quotient ring A. First of all, what we observe is that when you quotient by the non-faces of the simplicial complex, what we are left with is actually just the faces. So the monomials in this quotient ring would have a one-to-one correspondence with the faces of the simplicial complex delta. And the next thing is, following directly from this first point, that the Hilbert series of this quotient ring can be given in terms of the F vector of the abstract simplicial complex. And lastly, if we just consider the I skeleton, that is the faces up to dimension I, and we take this quotient ring of the I skeleton, it is same as taking all the graded pieces of A up to I+1 dimension. So this gives us some invariance of the quotient ring in terms of the simplicial complex delta. So this is, I hope the construction of the ideal we need is clear to everyone. And now,
does this have a name?
No, this does not as such have a name in theory. So it is just, some people call it as taking the Stanley-Reisner ideal and defining it as plus the powers of the variables. But as such, I have not come across any name in the literature for this quotient ring. Yes.
Excuse me, may I ask?
Yes, please.
This Hilbert series of A delta is another name for phase polynomial or something like that? Because it is generating function of
Yes.
number of thank you.
Yes, yes.
So I will ask my my main question at the end. Thank you.
Oh, okay. All right. Okay. Thank you. So heading forward to the main topic of concern, what do we mean by the Lefschetz properties? So now, if we have a graded artinian algebra A and a general linear form L, A is said to have the weak Lefschetz property if the homomorphism induced by the multiplication by the general linear form L has maximal rank. So this multiplication we are doing with each graded piece. So if we multiply the ith graded piece, it will be the map to the I+1th piece. And this map should have maximal rank for all I. Then we would say that this Artinian algebra satisfies the weak Lefschetz property. And an element which satisfies this condition for A would be called a Lefschetz element. And a strong Lefschetz property basically means we are doing this multiplication not just with the general form, but we are taking powers of the general form. So it is said to have the strong Lefschetz property, or the SLP, if it has maximal rank for all possible graded pieces I and all possible powers J. Now, how did the motivation come from? So the motivation actually came from Stanley's work in 1980, which was basically trying to prove that the strong Lefschetz property holds for a certain kind of quotients, namely the quotients obtained from Artinian monomial complete intersection. So basically, we are taking some I of the form x1 to the power a1 ... xn to the power an. Just powers of the variable. And then when we take this quotient, Stanley had proved that the strong Lefschetz property will hold for this. And all this actually stems from the hard Lefschetz theorem, which relates with, for those of us who are interested in cohomology theory, it actually sort of tells us that the Lefschetz properties mimic the cohomology ring of a certain kind of complex projective varieties. So this is having multiple applications in different branches. Moving forward from here, now we come to some observations or results. So given a standard graded Artinian monomial algebra, the weak Lefschetz property holds implies that A will have a unimodal Hilbert series. Unimodal Hilbert series basically means the coefficients of the series act like a peak. They will increase up to a certain point, and after that, they will keep on decreasing. So if A has the weak Lefschetz property, in fact, this also holds for strong Lefschetz property that A will have a unimodal Hilbert series. Then the next one is, we don't have to keep searching for any random general linear form. So this result in 2009 actually gave us the fact that this quotient S mod I has a weak Lefschetz property if and only if the sum of the variables itself is a Lefschetz element for S mod I. So this sort of gave us a characterization that we can just consider the linear form formed by the sum of the variables. So let's look at an example so that we can understand better. Suppose we're looking at the edge ideal of a path on 7 vertices, and then we are going to adjoin the squares of variables to it to define the ideal J delta. If we want to examine, for instance, the weak Lefschetz property at degree 1, that means we are going to multiply this L, which we're taking as a sum of the variables, and we're trying to see how the map looks from A1 to A2 at degree 1. So after multiplication, the associated matrix looks something like this. Now, this matrix itself, it's just on 7 vertices, but it has a dimension of 15 by 7. So as you can see, these matrices can get very large. So computing the rank to check for the Lefschetz property is not very easy. Hence, we have to come up with some alternative methods. And fortunately, we do have many results in this direction. That is what we will be focusing on. We first state a criterion which is particularly useful for checking for the failure using the Hilbert series. Now, using the Hilbert series gives us an advantage that we can use Macaulay 2 or such software to compute the Hilbert series directly. So the proposition is as follows. If we have an artinian monomial algebra and a general linear form, then just by observing the map, so we have the map which is in question, mu I, and then we take the co-kernel of that. So this map fails to have the maximal rank if and only if. So it's giving us a characterization that dimension of this co-kernel is greater than both 0, or if it's positive, the difference of the dimensions of these two pieces. Now, this observation follows directly just by taking cases, when is it not injective, when is it not surjective, and working out the dimensions. For instance, let's go back to the same problem we had at hand, the edge ideal for the path on 7 vertices. So when we defined the ideal J delta and we took L, the Hilbert series looked something like this. So this is the Hilbert series of A, and this is the Hilbert series of the quotient by the general linear form. So what we observe, for example, if we are looking at Lefschetz property from 1 to 2, what we do is we look at the dimension and we try to see the difference. So the dimension here, if it's going from 1 to 2, we are looking at the dimension of the second piece. So here it is 8 for the quotient. And then we look at the difference between these two. So 15 minus 7. Since these dimensions are equal, that means this difference is not less than this value here, which means the Lefschetz property does not fail in this case, okay? So here the Lefschetz property actually holds. So from that, what we observe is that...
Wait, can you explain? I'm sorry, can you just explain that really quickly?
Oh yeah,
again?
sure, no problem. So all that we need to do is if you're looking from 1 to 2, so here, the dimensions at hand are, this is the dimension of A1, A2, 7 and 15 respectively, and this is the dimension of A mod LA second piece, okay? So the condition we need is dimension at the second piece, which is 8, is it greater than the max of 0 and the difference of these two, which is 15 minus 7? In this case, since it's not greater than that, so we will say that the Lefschetz property does not fail. It holds. I hope that is okay.
Yes, so it's an if and only if?
Yes, it's a characterization. It's an if and only if case.
Thank you.
Yeah, no problem. Thank you for the question. Now, proceeding from here. So this particular kind of ideal, as someone had asked earlier, it's actually been analyzed in some other papers already. I would like to point that out. So there are some results related to the Lefschetz property of this quotient ring A. And moving forward from there, let us come to some characterization we would like to introduce. So we are trying to give a characterization of Lefschetz property in degree 1 for this quotient ring A, just by using the one skeleton or the edge graph of the simplicial complex. Now this result is as follows. So we are taking two cases. One case is if the dimension of the second piece is greater than or equal to the first piece, and the second case would be the other way around. So the first case says if the dimension of the second piece is greater than or equal to the first piece, means number of edges is greater than the number of vertices for the simplicial complex. Then Lefschetz property holds in degree 1 if and only if that edge graph has no bipartite components. And in the other way around, if the number of edges is less than the number of vertices, then we say that the Lefschetz property holds in degree 1 if and only if either if there is a bipartite component, it has to be a tree, or if there are non-bipartite components, all those non-bipartite components should satisfy the fact that the number of vertices in those components are equal to the number of edges in those components. So, for instance, let's go back to our running example, edge ideal of a path. Now, consider the edge ideal of a path on n vertices, and we define the complex as we did earlier. Let's look at the Lefschetz property. So the Lefschetz property always holds in degree 1 for this quotient ring. Now, how do we see that? For small values of n, it's not very hard to compute and check by hand. But for large values of n, something interesting that we can observe is that the edge graph of the corresponding simplicial complex will never have bipartite components. Okay, it will always have one triangle as part of the complex. And hence it can never be bipartite. So because of that, this will always have weak Lefschetz property in degree 1. Now, I would like to point out here, the simplicial complex itself was not the path, it's actually the complement of the path. So this is one interesting way of applying this result to come to conclusions about weak Lefschetz property in degree 1. Moving on from there, we come to the last part of my talk here. So talking about the weak Lefschetz property of something called a pseudomanifold. Now, introducing this terminology, it is basically just a d-dimensional manifold which satisfies some conditions. D-dimensional simplicial complex that satisfies some conditions. So the conditions are as follows. Each facet is a d-simplex. So for instance, we could just construct something of this form. So each facet here I am taking as triangles. All of them have the same dimension. They're all two-dimensional. And the next condition is that every dimension of d-1 simplex will actually be incident on just one or at most two facets. So for example, every edge on this figure is either part of two triangles or they are boundary edges, just part of one triangle. Okay. And the last condition here is that given any two facets, we can always find a chain of facets that link them. So if we start from this facet, for instance, we can move across and come to another facet. Okay, there is a path connecting two facets such that their intersection will just be a D-1 simplex. Now, we will say that a pseudomanifold is with boundary if it actually has got a D-1 simplex that is incident on just one facet, like the one I had drawn earlier. We had edges which were just part of one triangle. If such a case is not there, then we would say that it's a pseudomanifold without boundary. Lastly, before going to the main result, defining the dual graph. So the dual graph G star of the simplicial complex, we are defining it as the graph in which every facet becomes a vertex. And we would have two vertices have a common edge if and only if the corresponding two facets will share a D-1 simplex, which is also called as a ridge. So this is the next characterization. That is, whenever we have a D-dimensional pseudomanifold without boundary, that means every.
I just want to let you know you are about 1 minute over. So if you could wrap
up,
yes,
yes,
that'd be
sure,
great.
Sure, this is the last one. Yeah, thank you so much. Yeah. So if we have a D-dimensional pseudomanifold without boundary, then the WLP will hold in the last dimension, that is the D-1 dimension, if and only if the dual graph has no bipartite components. It'll be easier to demonstrate with an example. So I'll go on to the next part. And in case of pseudomanifolds with boundary, it was observed that the Lefschetz property would always hold in the last degree. Just to demonstrate with an example, this is the last part. So suppose we are taking the octahedron as the abstract simplicial complex. So this is actually a pseudomanifold without boundary because, as you can see, every edge is incident on two facets. Now, in this case, it's observed that the Lefschetz property is not holding in degree 2. The reason being that the dual graph of this complex is actually just the edge graph of a cube. And if we draw the edge graph of a cube, we can notice that it is bipartite by just shading the vertices. So if we highlight opposite vertices like this, we can actually get bipartite components. And because it has a bipartite component, we can see that Lefschetz property fails in degree 2 by the previous result. So that's, yeah.
Thank you. Thank you very much.
Yeah. Thank you.
We have time for 1 or 2 quick questions.
May I ask a question?
Sure.
Thank you very much for your very nice talk. The point is that I am working in a special case of this, which is called click polynomial, means the graph case. So
Okay.
from the graph case, I have this idea. I'm wondering that the roots of that Hilbert series, roots of polynomial, can be related to your problem, because in the click polynomial case, we know that all simple graph has always a click polynomial, and from the largest root we can get a lot of interesting combinatorial property.
Oh yes, yes, definitely, yes. If I
for
understand,
example, sorry to say, for example, chordal graph has always all roots real, and that implies this modal, unimodal, and even log concave. So I'm wondering that even if we have not all real roots, we still have this unimodal or log concave. So is there any result related to real roots of those Hilbert series?
Over the top of my head, I cannot directly think of any result I have come across about it. However, what I can point out is that this very first reference, the Lefschetz property, the book, that actually has got many results related to the unimodal Hilbert series and Lefschetz properties in it. So they have taken some cases, but I don't remember seeing anything related to the roots specifically in there. But I would be happy to discuss with you later. Yeah.
Yeah. I mean, just last question is that can we have any idea, a geometric idea, or in the case of graph for Lefschetz property? What does it mean in graph case?
So like if we are taking the edge ideal.
Yes.
Okay. So the geometric case, so basically when we talk about geometric case, we are actually looking at sort of the simplicial complex as such, right? The geometric realization of that, I believe that is what we're referring to. So directly speaking of the relation, I would say, if it is just by one observation we can directly make is because we are taking the sum of the variables as a Lefschetz element. So just for instance, let me just probably go back to one of the slides. Okay. Sorry, I need to go back to probably the first example. In simple terms, what we can observe is because the sum of the variables itself is a Lefschetz element. So in this case, this is if we are trying to see if multiplying by this sort of gives us Lefschetz property, right? So what we see is that if we take any vertex, for instance, is it incident? Which all edges is it incident on? That is what this map actually gives us. So if we try to, for example, if you're just taking x4 corresponding to the fourth vertex, multiplying it with L would actually tell us which all edges it is incident on. So one way of looking at Lefschetz property geometrically is looking at the fact that these vertices are incident on which all edges.
Thank you.